A cut on your hand at age 25 closes in 7 days. That same cut at age 55 takes 14 to 18 days. The reason is not what you think. It's not slower blood or thinner skin. It's a signal, a chemical broadcast your cells used to send flawlessly, a call between your skin and your immune system that has been fading since your early 50s. And once that signal drops below a critical threshold, your body stops repairing itself the way it was designed to. Most people assume wound healing slows because the body simply wears out, like an old car with a rusty engine. That's the story we've been told. Your doctor might say something vague about reduced circulation or aging tissue, and you nod, because it sounds right. It isn't right, not entirely. In 2016, a team at Rockefeller University, led by Elaine Fuchs, one of the most cited cell biologists alive, published findings in the journal Cell that overturned decades of assumptions. They studied mice equivalent to 20-year-old and 70-year-old humans. What they found was specific and disturbing. The skin cells in older animals weren't broken. They weren't dead. They weren't incapable of healing. They had simply stopped talking. The keratinocytes, the cells that form the outer barrier of your skin, had lost the ability to produce specific signaling proteins called skints. These skints are the language your skin cells use to recruit nearby immune cells to a wound site. Without that signal, the immune cells never arrive. And without the immune cells, the wound sits open, waiting, exposed. Think of it this way. Imagine a fire station where every alarm has been muted. The firefighters are still there, the trucks still work, but nobody hears the call. That's what's happening inside your skin right now if you're over 50. And the real question is, why does this communication collapse? What causes your cells to go quiet? The answer involves a cascade of failures that most physicians were never trained to recognize. To understand why your wounds heal slower, you need to understand what's supposed to happen when your skin breaks open. It's a 4-phase military operation, and every phase depends on the one before it. Phase 1 is hemostasis. Within seconds of a cut, your platelets swarm the site. They form a clot. That clot isn't just plugging a hole, it's releasing growth factors. Platelet-derived growth factor, transforming growth factor beta. These are chemical orders. They tell nearby cells, come here, now, and start working. Phase 2 is inflammation. Within hours, neutrophils arrive. They're the first responders. They kill bacteria. They clear debris. Then macrophages roll in. And this is where things get critical for your body after 50. Macrophages come in 2 forms. The research community calls them M1 and M2, though some scientists dispute the simplicity of that classification. M1 macrophages are aggressive. They attack infection. They clean the wound. M2 macrophages are builders. They lay down new tissue. They signal fibroblasts to start producing collagen. Here's what goes wrong with age. In a young body, macrophages switch from M1 to M2 within 3 to 6 days. The transition is smooth, efficient. In your body after 50, that switch stalls. A 2018 study from the University of Nottingham demonstrated that in aged tissue, M1 macrophages linger far longer than they should, sometimes 10 to 14 days. They keep attacking. They keep producing inflammatory cytokines like interleukin-6 and tumor necrosis factor alpha. Your wound stays in an inflammatory loop. Picture it like this. You've hired a demolition crew to tear down an old wall before renovation, but the demolition crew refuses to leave. They keep swinging sledgehammers. The construction team is waiting outside. They can see the site, but they can't get in because the demolition is still happening. That's what chronic inflammation does to your healing process after 50. The cleanup crew won't clock out. And this matters enormously because phase 3, the proliferative phase, cannot begin until inflammation resolves. Phase 3 is when fibroblasts arrive and start manufacturing new collagen. It's when new blood vessels grow into the wound bed. It's when your body actually rebuilds the structure it lost. A 2006 study from the University of Michigan, led by James Varani, measured collagen production in skin from adults aged 18 to 29 versus adults over 80. The reduction was staggering. Collagen synthesis in older skin was 68% lower than in young skin. Depending on who you ask, the figure ranges from 60 to 75%, but the direction is unambiguous. Your fibroblasts are producing a fraction of the raw material your body needs to close a wound. But this is only half the story. What happens at the molecular level, inside the nucleus of your cells, is even more alarming. Your fibroblasts aren't lazy, they're starving. Every cell in your body runs on a molecule called NAD+, nicotinamide adenine dinucleotide. Think of it as the fuel currency of cellular work. Every time a cell needs to repair DNA, produce collagen, send a signal, or divide, it spends NAD+. Here's the problem. Your NAD+ levels have been declining since your mid-20s. Research published in Frontiers in Endocrinology measured whole blood NAD+ concentrations across age groups and found a significant decline beginning in the 40 to 49 age bracket. Some researchers estimate a 40 to 50% total decline by age 60. The research is still evolving on this. Newer studies from the University of Copenhagen suggest the decline may be closer to 30%, but the functional consequence is clear. When NAD+ drops, your cells lose their repair capacity. Your fibroblasts can't produce collagen at the rate they once did. Your keratinocytes can't migrate to close a wound the way they did at 30. The DNA damage that accumulates every day in every cell of your body, from sunlight, from oxidative stress, from normal metabolism, stops getting fixed efficiently. If you've ever noticed that a small scrape on your arm takes 2 weeks to disappear instead of 4 days, this is what's happening inside your body. The cells at the wound edge are energy depleted. They're trying to do their job with half the fuel. But NAD+ decline doesn't happen in isolation. It triggers a second failure. When NAD+ drops, a protein called PARP1, which is responsible for repairing broken DNA, starts competing for whatever NAD+ remains. PARP1 consumes NAD+ voraciously during repair attempts. This creates a vicious cycle. More damage means more PARP1 activation. More PARP1 activation means less NAD+ available for everything else. Your cells are caught in a resource war, and wound healing loses. Now connect this to the Rockefeller finding. Those Skint proteins, the ones that keratinocytes need to produce to call immune cells to the wound. Producing those proteins requires energy, cellular energy, NAD+. When your keratinocytes are running on 50 to 60% of their normal fuel supply, they can't manufacture the signals. The communication dies. Not because the gene is broken, because there's no power to run it. If this is making sense to you, and you want to hear the third part, the part about what you can actually do to restore this signal, subscribe now. Because what comes next changes how you think about every cut, every bruise, every slow healing patch on your body. It's coming in the next few minutes. And here's what makes this worse. None of this matters if you don't understand what your immune system does or fails to do while you sleep. What almost nobody talks about is this. Your body does the majority of its wound repair between 11 p.m. and 3 a.m. A 2017 study from the Medical Research Council Laboratory of Molecular Biology in Cambridge, England, published in Science Translational Medicine, found that wounds sustained during nighttime hours healed 60% faster than wounds sustained during the day. The researchers tracked 118 burn patients and discovered that daytime burns took an average of 28 days to heal. Nighttime burns took 17 days. The difference was not marginal, it was enormous. Why? Because your fibroblasts follow a circadian clock. They migrate to wound sites fastest during the biological night phase. The actin proteins they use to physically crawl across damaged tissue peak in activity during those dark hours. Your cells are programmed to rebuild you while you sleep. But here's the part that makes this critical for anyone over 50. If your sleep is fragmented, if you're waking at 2 a.m., if you're getting less than 6 hours of consolidated rest, your fibroblasts never hit peak migration. They never reach the wound bed at full capacity. The circadian signal that coordinates their movement is blunted. Read that again. Your body schedules repair work at night, and if you're not sleeping through the repair window, the work doesn't get done. Historians still argue whether circadian medicine will become a standard part of wound care, but the evidence is building fast. A 2019 follow-up study from the same Cambridge group demonstrated that the gene BMAL1, a master circadian regulator, directly controls actin dynamics in fibroblasts. Mice without functional BMAL1 healed 60% slower, regardless of when the wound occurred. The clock wasn't just timing the repair, it was enabling it. Now stack these 3 failures on top of each other. Your macrophages won't switch from attack mode to repair mode. Your NAD+ levels are depleted, crippling cellular energy. And your fibroblasts, even when they have enough fuel, can't reach the wound because your circadian rhythm is disrupted. 3 signals, all fading, all interacting, all accelerating the slowdown you've noticed on your own skin. So the question becomes, if your body has these built-in repair mechanisms, and all 3 depend on signals you can influence, how do you restore them? Here is what the research points to. 4 interventions, each targeting one of the failures described above. Step 1. Fix the macrophage switch. The most reliable method documented in clinical literature is moderate intensity movement, specifically 30 minutes of walking at a pace that raises your heart rate to 55 to 65% of your maximum. A 2014 study published in the Journal of Applied Physiology by researchers at the University of Illinois demonstrated that regular moderate exercise normalized macrophage polarization in aged mice, meaning the M1 to M2 transition happened on schedule rather than stalling. The mechanism is straightforward. Movement increases blood flow to tissue, delivers anti-inflammatory signals like interleukin-10, and physically stimulates macrophage clearance. Do this daily. Morning is ideal because it synchronizes with your cortisol awakening response. Step 2. Support NAD+ production. Your body synthesizes NAD+ from precursors, primarily niacin, tryptophan, and nicotinamide riboside. Foods rich in these include chicken breast, salmon, green peas, mushrooms, and avocado. Dr. Charles Brenner at City of Hope National Medical Center has researched nicotinamide riboside extensively since 2004 and has published data showing that oral supplementation with 300 milligrams daily raises blood NAD+ levels within 2 weeks. Whether this directly accelerates wound healing in humans is still being tested, but the cellular logic is sound. More fuel means more repair capacity. Step 3. Protect your circadian repair window. Go to sleep before 11 p.m., not midnight, not 11:30, before 11. Your fibroblasts begin peak migration activity during the first cycle of deep sleep, which for most adults over 50 occurs between 11 p.m. and 1 a.m. If you're awake during that window, you're missing the most productive repair period of your entire 24-hour cycle. Eliminate blue light after 9 p.m. Keep your bedroom at 65 to 67 degrees Fahrenheit. These aren't preferences, they're biological requirements for optimal wound repair. Step 4. Supply the raw materials. A clinical trial published in Clinical Nutrition in 2005 demonstrated that supplementing with arginine, vitamin C, and zinc significantly improved pressure ulcer healing rates in older adults. The doses used: 9 grams of arginine, 500 milligrams of vitamin C, and 30 milligrams of zinc daily. Arginine is a precursor to nitric oxide, which your body uses to build new blood vessels at wound sites. Vitamin C is required for collagen synthesis at every step. Zinc activates over 300 enzymes involved in cellular repair. If even one of these steps was new to you, hit like. It tells the algorithm to show this to more people who need it. And most people over 55 have never heard any of this framed this clearly. Dr. Gary Fisher at the University of Michigan has been studying skin repair mechanisms in older adults since the 99 seconds. His published work confirms that collagen synthesis can be partially restored even in aged skin, using retinoic acid and mechanical stimulation. Your body is not beyond repair. It simply needs the right inputs. Here's what this comes down to. Your body was built to heal. That capacity didn't vanish. It didn't expire on some biological clock. What happened is quieter than that. 3 signals: the macrophage switch, the NAD+ supply chain, and the circadian repair schedule, faded below the threshold your cells need to operate. Nobody told you this was happening. No doctor flagged it at your annual checkup. No prescription addressed it. Because the medical system is built to respond to disease, not to the slow erosion of cellular communication that makes disease possible in the first place. I want to hear from you. Drop a comment below. Have you noticed wounds healing slower in the last 5 years? When did you first realize something had changed? I'd bet most of you have noticed, but never connected it to sleep timing or immune cell behavior. The cut on your hand is not a small thing. It's a test. Every time your skin breaks, your body reveals how well its internal communication is working. A fast healing wound means your signals are strong. A slow one means they're fading. You don't lose healing, you lose the signal. Share this with someone who's noticed their skin taking longer to recover. They deserve to know why. And if you haven't subscribed yet, you should. What I'm researching next involves the one protein that determines whether your skin scars or regenerates. That video is coming soon. Your body is still listening. The question is whether you'll start speaking its language.